Okay, so let me remind you where we stopped last time. So we're talking about affine Kac-Moody algebras. So we're going to use the explicit presentation of that. So that was g hat is equal to LG direct sum, a central term, and direct sum, a derivation. G was simple finite dimensional. So we had two notions. One was we said V had level K. A representation V had level K. If the center acts as K times the identity. And we also had the notion of an integrable representation. So V is integrable if the elements. So now I'll just do it in this special case. So xi plus tensor t power r act locally nilpotently. So the condition I gave yesterday was in terms of Chevalley generators, but it doesn't really matter. So act locally nilpotently for all I and all r. So I will go from 1 up to n, and r will be in the integers. And our goal was to classify irreducible integrable representations of g hat. Okay. So I guess I was calling this GE hat. So I'll keep that. Okay, so this goal is a bit unmanageable. We need a small finiteness condition. So we need a finiteness condition so Vishwanath told me yesterday, I forgot to say something in my definition of integrable. So we have to assume that so V is integrable. There's an assumption that I left out yesterday, which is that you have to assume that V is a direct sum of eigenspaces for the Cartan subalgebra. So the Cartan subalgebra we said was H direct sum CC direct sum CD. Okay? And by V mu, what we mean is all those vectors V and V which transform according to mu. Okay? So it's a sum of eigenspaces for the action of H. Plus minus, yeah. So the finiteness condition that I'm going to impose is we're going to demand that dimension of V mu is finite for all mu in the dual space. Without this condition, I don't know how to classify irreducible representations, integrable representations. There are examples of such modules, but a complete classification is not known. So then the theorem, which I proved a long time ago, was the following. So supposing I had V, irreducible integrable g hat module, with this restriction, so dimension of V mu is finite. Then one of the following must hold. Then either V has positive level, V has positive level, and V is isomorphic to what we were calling V lambda. Okay. So if you have an irreducible representation, and you have this condition, then it's clear that C acts by integers on the whole thing because it's irreducible. Schur's lemma tells you that it acts by a multiple of the identity on the whole thing. Okay? So it has either positive level, negative level, or zero level. So V has negative level. Implies that V is isomorphic to the dual of this representation suitably understood. Okay? So I don't really want to go into this. So this is called the restricted dual. Okay. These two representations are never isomorphic if lambda is not equal to a multiple of delta. Okay? And the third case, V has level 0, okay, in which case I want to be able to tell you what the representation is. Okay, so in which case V is isomorphic to what? Okay. So to tell you that, I should have answered a question that I asked yesterday, which was, how do I construct representations? So I want to give you examples of level 0 representations, which you remember are supposed to be like the adjoint representation. So there's a very cheap way to construct level 0 representations. Right? So what is this cheap way? What does LG look like? It looks like G tensor CTT inverse. Right? So more generally, let me take V to be any vector space. So v, in particular, V any G module. So then I take L of V to be V tensor CTT inverse. And I can define a G hat module structure on this as follows. So if I take an element in G hat, it either looks like this, in which case I just make X act on V, I do multiplication, or it looks like the derivation, in which case I take V and I make the derivation act on the second thing by T d by dt. And the center, well, I have no choice. I'm looking for a level 0 representation, so that better be 0. Okay. So these are called loop modules. And here's a trivial exercise. So if V is finite dimensional, then that implies G module. Then that implies that L of V is integrable. Okay. So I know how to produce now lots of examples of integrable modules, right? Because I have one for every G module. So this construction can actually be generalized a bit. I want to keep that theorem over there. So let me continue here. So a generalization is is as follows. So suppose now that V is any LG module. Okay? So it's only a module for the loop algebra. I'm not going to put in the derivation. Then this can be made into a level 0 module for the affine algebra by a very similar construction. By. So let me write it over there. Conserve energy in this heat. So this is equal to, so you make X tensor F act on V now. G. So this V is now a module for LG, right? So this makes sense. And then I just multiply it over there. So this is just a bookkeeping so that I can make my derivation act. Otherwise, my derivation won't act. Okay, so it's to go from LG modules to G hat modules. G hat modules have this derivation built into them. So this is just a cheap trick to go from, to get a graded module with a D action out of this thing. And so these are also called loop modules, and all these formulas stay exactly the same. And again, if V is a finite dimensional LG module,
V is an LG module, but it's not going to be presented as a tensor property. So why do you try to do this?
oh, I'm sorry, this is on LV. For L, okay, so we turn it into a level 0 module, LV. So it's going to be on V tensor CTT inverse. Yes, I agree. That's right. No, that's not what I meant. So I start with an LG module, and then I look at this vector space, and then on this vector space, I define an action of the affine Lie algebra. So it's not on the original space. That's wrong. Okay? Yeah, I agree. So, but what I meant here was L of V. Okay. So you notice that over here, I'm not saying that if I have an irreducible module, I'm getting an irreducible module over here. It's because I don't, usually. So now I can state the theorem, complete the statement of the theorem. So I'll say a little more about that example, but let me complete this. So V as level 0 implies that V is isomorphic to an irreducible submodule of some LV tilde, where V tilde is an irreducible finite dimensional module of LG. Okay. So this last part is actually out of joint work with Presley, sometime in '87. So what does this, so let's look at this theorem. So it tells me that if I want to understand positive level modules, I have to understand V isomorphic to V lambda. There's lots of literature. This has been studied by lots of people. So this is a well understood thing. You have things like Wildcat's character formula for them and so on. This is the dual picture. It's easy again. And so now what I want to explain is this picture. So this picture tells me if I want to understand level 0 modules, I better understand finite dimensional modules for the loop algebra. Okay. So that's why one sort of shifts focus to some extent and drops the derivation and only thinks about finite dimensional modules. So, but let's look at examples of this, other examples of this construction. So what exactly is going on over here? So what's an easy way to construct representations of LG? So let's look at how to construct construction of finite dimensional representations of LG. So that we've agreed now that what we want to do is to understand finite dimensional representations. So how should we construct them? Well, so LG is G tensor CTT inverse, right? So this is a polynomial. Once you have a polynomial, you can evaluate it at some point, right? So supposing I take A and C star, I can look at the evaluation map at A, and I go down to G. So this is X tensor F going to F of AX. Right? This is a homomorphism of Lie algebras. So if I could take any representation of G, I can pull back is a representation of LG. Yeah? So given any representation of G, I get a representation of LG, finite dimensional representation. Right? V is irreducible. This implies F star A, V is irreducible. Question, are there others? Okay. So now what is my next goal? And this is going to be critical now, is to classify irreducible finite dimensional representations of LG. So this theorem tells me I really need to understand that, so now I'm going to go understand that. And I'm going to give two different proofs of that. One which is really quite elementary. So we're going to see two different proofs of the classification theorem, which I'll state. So what's the reason for doing that? So one proof is quite elementary, and it works for these more general algebras which people are now studying. They're called map algebras. And so these are algebras of the form G tensor A, where A is, say, the coordinate ring of an affine variety, for instance. So this is a Lie algebra in the obvious way. You take the commutator here and you multiply that. Okay? But this proof sort of doesn't lead to anything deeper. It's a nice proof. It solves this particular problem, but it doesn't go anywhere further. In particular, it doesn't work for quantum algebras. So it doesn't work for quantum affine algebra. So the second proof works in the quantum case as well. And it sort of introduces new elements and new ideas which are critical for other things. So it introduces new ideas which are critical for a more general study of our category, and also of the structure, and also for the structure theory. So let's look at the first proof, which is very simple. So let me state, so I guess I should state the theorem first. So for the theorem I need notation. So we'll let psi be the set of all finitely supported functions from x to p plus. I should tell you what x is. So x is the affine, underlying affine variety. So working with the context of G tensor A. So x is our set of points. Okay. And we're demanding that if you take an element psi and psi, it's a function. If you wish, you can just, if in the case when A is CTT inverse, you could just take x to be C star. Okay. So, so what we're saying is if you have an element psi, then psi of x is 0 for all but finite, it's a 0 weight for all but finitely many points. So then the theorem, so this is now by now due to many people. In this form it was, well, there was, in this form there was originally approved by Ishwar Rao and then Batra, Lau, and so on. So it says that the irreducible representations of G tensor A are indexed by elements of psi. So you take any function with finite support from x to p plus, that gives me an irreducible representation, and conversely. And how is the and what is the so if you take psi, what is the representation you associate to it? You associate to it. So so let me give you a small example. So I have psi. So this is a finitely supported function. So what is this? What is the smallest example? It's when it's supported, say, at one point, right? So supposing I have psi A equal to lambda and psi x equal to 0 otherwise. Okay. So what is a point in my variety determines for me a maximal ideal in my ring, right? So let M be the maximal ideal in the coordinate ring A. Okay. So the associated representation to this thing is just V lambda. We're working with G. It's a simple G module. And the action of x tensor A, no, A is bad notation. The action of x tensor, let me call this x naught. So the action of x tensor A on V will be the evaluation along this maximal ideal at A xv. Here A is an A. So what? So let's see. This is obvious. This is poorly written. So maximal ideal in A corresponding to the point x naught. Okay. And what do I mean by Fm at A? I mean you take Fm. So Fm is you take A to A mod M. Yeah? A mod M is C. Right? We're working always over the complex numbers. So this is our homomorphism. So x tensor A. So these are called evaluation representations for this reason. Okay? Is that vaguely clear? Sorry, is there a question? Okay, so now, so this is the simplest example when my function is supported at one point, right? Supposing my function was supported at 2 points. So now let's supposing I have psi x1. So let's call psi x0 lambda 0 and psi x1 equal to lambda 1. Yeah? And we'll call the maximal ideals, let mi be the maximal ideals in A corresponding to xi, I equal to 0, 1. Okay? Then the associated representation is now going to be on V lambda 0 tensor with V lambda 1. This is a tensor product, there's G modules, and the action will be given by, if you take X tensor A on V tensor W, or V0 tensor V1, this will be Fm0A X V0 tensor V1 plus V0 tensor Fm1A tensor. So you evaluate according to the maximal ideal that you pick. So the generalization is clear. I won't belabor the point. Okay, so this is the classification theorem. So this is stated in complete generality for G tensor A. These are also known for what are called twisted map algebras or equivariant map algebras. Again, I won't go into that. How do you prove this theorem? So the first proof. So supposing we're given V irreducible finite dimensional representation of LG. So what do we have? So we have a map from G tensor CTT inverse to endomorphisms of V. This is what you mean by saying that you have a representation of your loop algebra. Well, this is a finite dimensional space, right? Because V is finite dimensional. What does that mean? That means the kernel is an ideal, so the kernel of rho is an ideal of finite codimension. Okay. So then what is the next thing you would do? You would want to understand what ideals of finite codimension are in this Lie algebra, right, to be able to use it in any sensible way. So then it's a little exercise using the representation theory of simple Lie algebra, so it's an exercise sort of worth doing, is that any ideal, this is, I'm writing CTT inverse, this could just as well have been G tensor A, okay? So any ideal in G tensor A is of the form G tensor A by J, where J is an ideal in A. As long as G is simple. This is not true for an arbitrary Lie algebra, of course, because those can have ideals, but as long as G is simple, the statement is true. And it's really a nice proof, as I said, using representation theories. Okay, so then what does one do? So we know, so we have this finite dimensional Lie algebra. Yeah.
G tensor J?
Sorry, yeah, I mean G tensor J, thank you. Yeah, I'm getting ahead of myself. So that means now, so this implies that we have an injective map zero to G tensor A by J, okay, to endomorphisms of V. Right? because G tensor J went to 0, it for the first homomorphism theorem, it factors through to give me a representation of this. And then there is this beautiful result in Bourbaki, which says, so there's a result, Bourbaki, which says that a Lie algebra which admits a faithful finite dimensional representation is semi-simple. Okay, so here's a Lie algebra. It has a faithful finite dimensional representation. So I get that this is semi-simple. Okay? That means it's a direct sum of simple Lie algebras. So G tensor A over J is isomorphic to a direct sum of simple Lie algebras. It doesn't tell you what simple Lie algebras, but it tells you a direct sum of simple Lie algebras. But of course, what would we want this to be? We have a Lie algebra G floating around, and we certainly don't want this to be anything ridiculous. We expect this to be just direct sum of copies of G. So the question is, how do you prove that? So for that, well, let's look at this algebra A by J. Okay. So basically what you have to prove is, so what one proves is that A by J is a semi-simple commutative Lie algebra. Commutative associative algebra. That means, but semi-simple algebras are just direct sum of, sorry, yeah?
Any Lie algebra can have faithful.
Finite dimensional.
Irreducible also?
Irreducible also. Faithful, irreducible, finite. Yeah, that is Ardo's theorem, but here this is. Yeah, so then you prove that A by J is a semi-simple commutative associative algebra, but that means it's just a direct sum of copies of C. Okay. And that means that G tensor A over J is a direct sum of copies of C. G. Okay. So how do I get to this from this? You just use, so this is a finite dimensional algebra, so you write it as a direct sum of the idempotents. So you use the structure theorem for associative algebras. Okay? So now I've got this as a direct sum of copies of G, and again, in an elementary course in representation theory, you know that if you take the direct sum of two Lie algebras, the irreducible representations are tensor products. So essentially this is the proof. Okay? So I mean, this is not supposed to be a complete proof. This is supposed to be a sketch of the idea of a proof. So a direct sum of copies of G, and this implies that any irreducible representation is isomorphic to a tensor product of irreducible representations of G. Okay. So then this can be completed. This is essentially complete, and it's as complete as I intended to be at this point. Is there a question? It's okay. All right. Okay, so that's the first proof. And although so this proof actually, I think, is really motivated by this observation, and this result was dug up by Michael Lau. So the proof of this theorem in this form is actually only in 2009 or something like that. But the original theorem was proved in 86. So, and that proof, while it's very complicated, actually takes us to nicer places. Can I stop for a few minutes to cool off? Thank you. So we'll have our break and start at 10:20 maybe. So. Yeah. I just need a few minutes to dry out. Okay, so I probably shouldn't have erased this proof completely. But anyway, so the crux of this proof was that this algebra G tensor A over J by Bourbaki, one knew that this was a semi-simple Lie algebra. Okay? So now supposing, my goal is to explain why this proof in some sense is not good enough. So supposing we were working with UQ of G hat, right, in the quantum case, where there is no underlying Lie algebra. So I would still have an irreducible finite dimensional representation of it, but I wouldn't be able to say anything intelligent about the kernel. There is no analog of the theorem of Bourbaki available to me over here, because there is no underlying Lie algebra featuring. So this proof just absolutely fails in the quantum case. Okay, so in that sense, this proof is not strong enough. So this wasn't really the original proof that I'd given, so because I was much more naive at that point, and so I did it in the obvious way. So let's talk about the second proof. And this proof will work, we'll see, works both for classical and quantum in almost the same way. So we have our irreducible representation. I'll stick with, so we have our irreducible representation, but it's not going to work for map algebras. So I'm going to do this to V, irreducible and finite dimensional. So the last two lectures I said I kept talking about how one would approach classification. So you would take V, you would take V0 in V, let's call it V in V, which is an eigenvector for this, for H. And what else can we assume? I claim that we can assume that n plus tensor CTT inverse has to kill V. Remember, we defined n plus yesterday for an arbitrary Kac-Moody algebra. So over here, you can do it for this. So why can I do this? Well, so I have my vector V. It had some weight lambda, right? If I apply x alpha V to it, and I calculate its eigenvalue, it's lambda plus alpha, right? I can have only finitely many. So since V is finite dimensional, implies that V has only finitely many eigenspaces. And so at some point implies there must exist some eigenspace let's say mu, such that mu plus alpha is not an eigenspace for any alpha in P plus, for any positive root. Okay. So it really is the same proof. So if you understood the proof for finite dimensional Lie algebras, there is no difference from that proof here. So I've picked what I like to call a highest weight vector. It's also called a loop highest weight vector. It's an eigenvalue for the Cartan, and this thing kills it. Okay. This is, because now we're working with L of G, so there's no center or no derivation. So this is H in H. Yeah. And of course, And I have the obvious relation, and I also, since it's finite dimensional, from SL2 theory, I have the relation that xi minus raised to lambda hi plus 1 on V, let me call this V lambda because I'm bound to stick in the V lambda at some point, V lambda equal to 0. Now, again, if you review your proof of classification of simple representations for simple Lie algebras, this is more or less the end of it. Once you have this, then there's really nothing more that you can do. Okay? But in our case, let's just do a small calculation, and we have more elements. So supposing I look at xi plus tensor t on xi minus raised to lambda hi plus 1 on V lambda. On the one hand, it's 0, because this element is 0, right? On the other hand, what can I do? What is the usual game you play? You change the roles of x minus and x plus, right? So I can move this xi plus over here, and then there's a cost to doing that. So this is equal to xi minus raised to lambda hi plus 1 V lambda xi. So this is xi plus tensor t V lambda. And then there's a certain commutator which I will get. And if I work at that commutator, I'm not going to write down the coefficients precisely, but what I'll get is something like this. So I'll get xi minus raised to lambda hi. And I'll get a commutator of those two, which is hi tensor t. And I'll get another scalar multiple, xi minus raised to lambda hi minus 1 xi minus tensor t V lambda. Okay? Yeah, that's right. So from now on, just take mu equal to lambda. This was supposed to be why I could choose something like that. So let's look at this absolutely horrendous equation. So what is this? Well, we've said that xi plus, that lives in n plus. So n plus tensor t acting on V lambda is 0, right? So this is gone. But I have no relations which tell me that this is, so now I'm getting a new relation which is actually 0, right? So I'm getting, so this gives me a new condition which I sort of don't know how to handle at this point. So we get that some scalar multiple, so xi minus raised to lambda hi tensor t, plus xi minus tensor lambda hi minus 1. So never mind the scalar multiples, they're definitely non-zero. Xi tensor t on V lambda equal to 0. So I don't know what to do with this condition. I don't know how to understand it. So what is the obvious thing to do? I apply this once more, right? And I keep applying it. Okay. So this is where we begin to have a nervous breakdown, because you try to do these calculations and you try to do them by hand. So I'm going to, so the calculation you have to do is the following. So let me write it abstractly. So supposing we have our, so let me remind you of certain facts. So supposing we have our, so we know that our Lie algebra G, for instance, let me call it A. Supposing I have my Lie algebra A, and I can write this as B direct sum C, right? As a sum of two Lie algebras as vector spaces, though. B and C are Lie algebras. Then we know that we can write U of A as U of B tensor U of C. This is Poincare-Birkhoff-Witt. Okay. And then what you can do is, for instance, you could choose to make B special. So you could write this as U of B, direct sum, oops, the u of A times this C. Right. What that means is you isolate u of B, and then you take the ideal in u of A generated by C. So the Poincare-Berkowitz theorem tells you that this is equal to the direct sum of these two vector spaces. And then you can take the projection from u of A to u of B. This is a projection. I'm not claiming these are Lie algebra maps or associative algebra maps, but these are vector space maps, and I do have these. Okay. So this is something you can do. And then, so this is what I want to do. So in my context, what I want to do is to look at the element xi minus plus tensor t power r. I don't want to write divided powers, power r, times xi minus power s. Yeah? No, same r. And I want to write down projection onto u of LH. So I'm writing L of G. So what am I doing? I'm writing L of G as L of n minus. This is n minus tensor CTT inverse plus L of H plus L of n plus. And now I'm taking u of LG and I'm trying to look for its projection onto u of LH. Right? Following this idea, I do have a projection and I'm trying to identify its projection. And why am I taking these two to be equal? What will happen then is, what will the correction term be for such a thing? The correction term, well, this has total eigenvalue for H being 0, right? So where will the correction term lie? This will actually look like something in u of LH plus something which lives in u of LG and plus tensor CTT inverse. In fact, and then over here it will be the, so this is the left ideal generated by this and the right ideal generated. So this is something you see when you're doing this Harishchandra homomorphism business. It's exactly like that. You're picking out the thing that goes to the Cartan subalgebra, and you're observing that this will kill the highest weight vector, for instance, in the Verma module. So this is an identical kind of argument. Okay? So what I want to do is to pick out this projection. Okay? And because I'm simple-minded, I'm going to try and do it by a brutal calculation. Right? I'm going to rewrite this thing. So let me write down the answer. For instance, so for r equal to 1, it's a simple answer. So for r equal to 1, what am I doing? I'm doing xi plus tensor t, xi minus, this is equal to xi minus xi plus tensor t plus hi tensor t. Okay? But if I do the next step, squared, then you'll find, so I don't want to write down this term. And when I try to write down this term, I get something like this. 1/2 plus minus maybe hi tensor t all squared. Okay. And if you try to do this calculation and you hope to do it correctly, it takes the better part of half a day. And then you try to do the cube and you say, okay, I'm going home. So, but then luckily, Garland had this absolutely amazing paper called The Arithmetic Theory of Loop Algebras, where he did this in complete generality. Where he wrote down, so it's a business of writing things in Poincare-Berkowitz. So he wrote down how to rewrite an arbitrary expression of this form. I keep writing divided powers, xi minus to the s equal to, and you rewrite it in the form that I wanted it. So in the form of u of LH plus, according to the decomposition, u of Ln minus tensor u of LH tensor u of Ln plus. So then you sort of abandon this calculation, and you're very glad that somebody else did it, and I'll tell you what the answer then is. And actually, once the answer is written, it's a very, very pretty answer. So this is a work of Garland. So, so the projection of, so I'm a bit worried about my signs at the moment, but anyway, of xi plus tensor t to the r, xi minus tensor 1 to the r on to LH is the element PIR given as follows. So we'll write it as a generating series. So let me do that. So this is summation PIR u to the r. Here for the moment I'm taking r greater than or equal to 0. And this is equal to the exponential of summation HIR u to the r greater. So what does this mean? This is a power series. Yeah? This is a formal power. This is a formal exponential. So you just open, right? So you just think of, so it's 1 plus this infinite sum plus the square of the infinite sum and so on. And you equate coefficients of u to the r on both sides. Okay? So if you so example P1, PI1. So PI0 will be 1. And PI1, well, it can only come from the first term, and then it can only come by taking r, right? So r equal to 1. So that's HI1. PI2, how can it come? Well, it can't come from the constant. It can come from the first term by taking HI2 over 2.
So HI1, HI2 and so on are...
Oh, sorry, HI tensor t to the r. Yeah. Sorry. So this is HI tensor t. Okay. The second one will come from doing HI tensor t squared over 2 plus HI tensor t all squared over 2. Okay. And so you can calculate. Yeah. I thought there should be a minus sign, but I couldn't see it over here, so I didn't put it in. Over here it doesn't show. So, yeah, I'm not sure what happened to the minus sign, but it seems to have vanished at this point. This is actually a well-known formula in the theory of symmetric functions. Okay, and this is the formula, if you think of these as the power sums, then these are the complete symmetric functions. Or I might have got it the other way. One is the power sums and the other is the complete symmetric functions. And so this is, and these things, I mean, symmetric functions are usually associated with AN, Lie algebras of type AN. The amazing thing over here is that these appear in Lie algebras of all types. Okay. And these things that, these are actually part of the canonical basis of Lustig for affine Lie algebras. So these are sort of very important functions which show up. There are quantum versions of these. So this was done by Garland, and the quantum case, Presley and I did that later in '97. So we have the analogs of all these things. Okay. So let's make further observations about these P's, because they're really quite critical. So you notice that so obviously the P's are defined in terms of the H's, right, with the denominators. But if you look at this, so if you have the P's, you have HI tensor T. If you have PI2s, if you have this and you have this, then you've got this, right? In fact, they're integer, so you get an integer multiple of this is what will give me HIT squared. Okay, so the point is that the algebra generated by the PIs is exactly the algebra generated by the HIs. By HI tensor T power R, and that's actually equal to U of LH. But what is more important is that the monomials in the PIR form a Z basis for U of LH. Okay. The monomials here don't give you a Z basis because you can't reconstruct the PIs. So what these PIs are like, so again, if you think in terms of characteristic P, when you think of the Costan-Chevalley form, Z form for UG, right? You have these divided powers, x alpha power R, alpha root. But when you work in the Cartan bit, you have to take these binomial coefficients, right, to get a Z basis. Otherwise, you don't get the Z basis that you want for your enveloping algebra. And these P's are the analogs of these things. So they're related to constructing Z bases for the enveloping algebra, and in the quantum case, to constructing the Z basis and the lattice, which allows you to go to roots of unity. Okay. So this is Garland's amazing result. And once we have Garland's result and all these comments, then let's see how to finish the proof. So we wanted to analyze. Oh, the AC is back on. The condition that xi1 plus tensor T power R, xi minus power R v lambda equal to 0. But Garland tells us what this is. This is the same as saying that equal to 0, in fact, if R is bigger than lambda of HI. Okay. And Garland tells us that this is the same as saying that PIR is equal to 0 for all R bigger. So I was trying to understand this condition. So I was trying to understand what it meant to say that this was 0, right? And now I've understood it by saying that certain elements in my enveloping algebra kill my element V lambda. So elements of my enveloping algebra. So, and now what about the cases where PIR is, so it's a simple exercise, so I'll leave it as an exercise, that the PIR of V lambda is always a scalar multiple of V lambda. Okay. So what we know now, so where for some DIR in C. So, summarizing, what have I got? At this point, I've proved the following lemma. Supposing V is an irreducible finite dimensional representation of LG, there exists a non-zero element V in V such that the following holds. H of V is equal to lambda HV, sufficiently big. So actually for all R bigger than, for all R such that absolute value of R is bigger than lambda HI. So I've always been working with positive things over here. How do I produce a negative? Right? My affine algebra goes in both directions. I can't change R to minus R, but I can change T to T inverse. Okay? And so that gives me my condition on the negative R's. Okay? So let's form, we had our favorite power series, PIR u to the R greater than or equal to 0. And so now what I'm saying is that this is really, when it acts on V lambda, is really acting as a polynomial. Right? This is actually a polynomial. So I'm saying that if I have a finite dimensional representation, for every index I have a polynomial. These are called the Drinfeld polynomials. Okay? And this polynomial I'll call pi I. Okay? There's still something missing over here, and there will be, so actually I better call that pi I plus, and similarly for r less than or equal to 0, I have pi r u to the minus r will be pi I minus, right? Times v lambda, yeah. Mm-hmm. Okay, so but there is still a certain, I mean, everything is supposed to be very rigid. So I've got my lambda, I've got that this is 0 for all r bigger than this, right? So what does that tell me actually about the degree of this polynomial? It's supposed to tell me something. It's supposed to tell me that the degree of this, so this degree of pi I is exactly equal to lambda of hi, pi I plus or minus. Okay? There's still too much freedom. This pi I plus and pi I minus are not independent. Okay? So in fact, I think the relation is just that pi I plus of u is equal to pi I minus of u inverse or something like that. So anyway, so there is a tight relation. There is no freedom at all. Okay? So the final result then is, so now the result will look different stated in this way. So what I want to tell you is how it's the same. So then the theorem is the irreducible finite dimensional representation of LG implies that V is given by an n-tuple of polynomials. Pi 1 up to pi n. These are polynomials with constant terms. So these have complex entries with constant term 1. Okay. And conversely, any such n-tuple determines V. So I'll tell you how it determines V in a minute. This theorem formally, of course, looks very different from the theorem I stated earlier, which was given in terms of finitely supported functions. So I want to make the connection with that. But I want to make some comments. So the proof that I gave you in the classical case goes through almost verbatim this part of the proof. This part won't. I'll tell you about that. This part of the proof goes through verbatim for quantum affine algebras. Okay. There's absolutely no difference, as it turns out. This is because I haven't probably remarked, but just like affine algebras have two presentations, quantum affine algebras has a second presentation as well. Have a presentation analogous to the explicit realization. So everything is always more unpleasant when you're working in the quantum case because you have to keep track of powers of q. So even these elements PIR, you have to put in powers of q in some clever way for everything to work. But once it's all done, then it works exactly in the same way. Okay, so let me tell you how, in the classical case, how to produce V. So what I want to do is relate this theorem to the original classification theorem, so to the original statement. in terms of finitely supported functions. Let's do SL2. That's for the most, that's always enough. In which case, I have a single polynomial pi. So how am I going to produce? What do I need to do? I need to produce a finitely supported function psi, which will go from C star to P plus. And what is P plus for SL2? It's the non-negative integers, right? So given my polynomial, how do I produce my psi? I need to produce a finite set of points, and on each point, with each point, I want to associate an integer. So what do? You factorize your polynomial. Once you factorize it, you take the distinct set of roots. That's your finite set. And for every root, you'll write down its multiplicity. And that gives me my finitely supported function, right? So you take pi, you write pi out as 1 minus a1u to the r1 into 1 minus aku to the rk, where the ai's are all distinct. This corresponds to taking different points, right, in my thing. And then I send ai to ri and a to 0 if a is not equal. And so I have my representation. Now, if I was working for an arbitrary Lie algebra, what would I do? What is the game I would play? So now let's do arbitrary g. I'm given pi equal to pi 1 up to pi n. So how do I produce my finite set of points and dominant integral weights? I'll factorize. I'll look at the product of pi 1 up to pi n, right? And then I'll write that out as 1 minus a1u. I'll just write out its roots, right? So let a1 up to ak be its roots, right? Now with a1, what I have to do now is to associate a lambda 1 in p plus, right? With each point, I have to associate a dominant integral weight. And what point will I associate to lambda? So what is the weight that I'll associate to it? I'll take a1. I'll look at its multiplicity in pi 1, how many times it occurs in pi 1, how many times it occurs in pi 2, and write it down. So then lambda 1 will be equal to summation ri omega I, where ri is equal to the multiplicity of a1 in pi I. Same game with a2. You look at the multiplicity of each root in each polynomial. So, and then you take the tensor product, and then that's good. Now, and this part, however, is a complete failure in the quantum affine case. Okay? And the reason, in some sense, the reason it's a complete failure is because this factorization doesn't take into account q at all. It's a factorization over the complex numbers. It doesn't see q. So this part fails miserably. So in particular, although this theory, so what you can prove, this theorem remains true. That if you have an irreducible representation, you have polynomials. If you have polynomials, you have irreducible representations. What doesn't remain true is the proof of how you get those irreducible representations as a tensor product. Okay? So that means so what I want to talk about tomorrow briefly is what goes wrong and what kinds of problems one studies. And so in the quantum case, there is no nice understanding of all the irreducible representations like there is over here, okay? Whereas just a nice tensor product. So I want to just say some things about how about what's happening in the quantum situation. And And so the last point that I want to make here is the fact that these PIRs are really very important. So let me take the time to say that properly. So let's look at U of LG, or in fact U of G hat. So we're going to define the Z form. So UZ of LG is the Z algebra, Z subalgebra, subring, generated by elements of the form x alpha power x alpha tensor T power K all raised to R, where alpha is a root and R is an integer. Remember that this means divided powers. It's this raised to R divided by R factorial. Okay? So originally when Constant and Chevalley gave us a Poincare-Birkhoff type basis for this algebra. Okay? So what Garland does is the same. So we have a Poincare-Birkhoff basis for this algebra. The Z-span of ordered monomials. Chalk small. So ordered monomials of the following. First you write down all the, so you write down x beta 1 minus tensor T power S1 and so on, x beta n minus tensor T power Sn. These can vary. And then you write down all these P1, R1, P, N, Rn. And then you write down x beta 1 tensor T power K1 to x beta n minus tensor T power K. I mean, each beta can appear more often with varying powers of T, but it's just too horrible to write it down, is a Z basis. Okay. Why is this good? You then tensor up with the field of characteristic P, and you get modular representation theory for affine algebras. Yep. Once you have a Z basis, you can take UZ of LG, or UZ of G hat as well, and then you tensor with Z and a field of characteristic P. Okay. You can talk about the representation theory of these algebras. And in fact, you can deduce conditions under which, so it's known conditions under which finite dimensional representations also have Z lattices. If you go to the quantum case, if you're working with UQ of LG, then instead of UZ, you look at UZQQ inverse of LG. Okay. And then you play this game. You don't tensor with the field of characteristic P, you put Q to be a number. You make Q act on C via epsilon. Epsilon is a complex number. Okay? And then when epsilon is a root of unity, all kinds of interesting things happen. If epsilon is not a root of unity, it's all generic. So these P's, and this theorem remains true, that you have a Poincare-Birkhoff type. Poincare-Birkhoff bases are also essential in these canonical bases. These things play a role in the canonical basis. Okay? So that's all I want to say about this. So tomorrow is going to be entirely about the quantum case. So it's not going to be it's not going to be very detailed or with proofs. It's sort of going to be an overview of what people find interesting in the quantum situation. And then that's it. Thank you.